Hey y'all, in today's video we're going to connect E back to delta G, which we learned about back in thermochemistry way back in the day. Today's video is mostly just learning how to do it conceptually, but then I'm also going to show you how to use an equation that is on your formula sheet that you don't have to memorize, and we're going to connect the two that way as well. Let's go ahead and get started. The first thing to keep in mind is that E of a cell, when it's positive, represents a cell that is spontaneously going to move in that forward direction. If the E is positive, a spontaneous cell would also therefore have a negative delta G, which we learned about back in thermo. Delta G being negative is a spontaneous process. So a positive E and a negative delta G both represent spontaneous processes. The only difference is with delta G, we're using the units kilojoules per mole, whereas with E, we're using the term volts. So with a positive E and a negative delta G, our battery will function. With a negative E, therefore a positive delta G, the battery will not function. It won't be a functional battery. The math I'm talking about is an equation that's on your formula sheet. On your formula sheet, there's an equation below delta G under thermochemistry that says delta G is equal to negative NFE. N is the number of moles of electrons transferred per mole of reaction. F, Faraday's constant. E, the voltage at standard conditions of your cell. So with this, mathematically, we can connect delta G to E. Keep in mind, that negative in the front of the NFE makes a big difference because that's what's going to make your positive G's negative E's and your positive E's negative G's. When we talk about spontaneity, keep in mind that it is a binary system. You are either spontaneous or you are not spontaneous. And all we're looking at there are the signs of delta G and E. So spontaneous or not has nothing to do with the actual values of delta G or E. It's just whether they're positive or negative. And that tells us something, but it doesn't tell us a whole lot about how it's actually going to work. When we look at the thermodynamic favorability, on the other hand, that does tell us quite a bit about the process itself, as a more positive or more negative value could be more thermodynamically favorable or less thermodynamically favorable. And so the idea here comes back to the quantitative idea of a sliding scale. Thermodynamic favorability is not a binary system. So we're going to use thermodynamic favorability a lot more often when we get into the quantitative approach with that equation that we just talked about, delta G is equal to negative NFE. And what you can see here is that as the delta G gets bigger in magnitude, so will the E. As the delta G gets smaller in magnitude, so will the E. It tells us a little bit more about the whole system. So let's do a quick practice problem where you're going to connect E to delta G. Here I've got a battery, which is made of copper and zinc. All right, so it's a zinc copper cell. I need you to tell me what is the E value of the cell at standard conditions, and then we need to calculate the delta G. So let's go ahead and do that using all the things we've learned before and then the equation that I just taught you earlier in this video. Go ahead and get started. I'm going to let you do this one on your own. If you get lost or stuck, come back to me when you're done and we'll talk about it. All right. Now, the one trick to this one is that we need to make sure we're using the correct units. Be careful here. Because of the fact that our units of Faraday's constant and our units for delta G may or may not match, we need to make sure they do before we continue on the process. When we look at this example, the E at standard conditions is 1.10 volts. When we're going for that to delta G, what we're going to do is we're going to say the number of moles of electrons transferred in the reaction. Well, that's going to be 2. Zinc and copper, when the reaction is balanced, each give up and gain 2 electrons. So that's a total of 2 electrons transferred per mole of reaction. So that N is 2. The F is Faraday's constant, 96,485 coulombs per mole of electrons. Then we get to voltage. Now, one thing to keep in mind, voltage has a unit, which is joules per coulomb. So a volt is 1 joule for every 1 coulomb. That means that in the end, our number that we get is in the units of joules. All right, be careful with that. So we take our 2 moles of electrons, multiply by the 96,485 coulombs per mole of electrons, multiply by the voltage at the standard condition of 1.10 volts or joules per coulomb, and we get a delta G value of negative 212,267, which, if I round it to sig figs, would be 210,000 joules. That leads us to kilojoules, all right, which would be negative 210 kilojoules. So here we have it. We've used the equation to predict the delta G of our battery. This is important. Delta Gs of batteries that function are always going to be negative, and not just a little negative. They're going to be really negative. All right. In order for a battery to work well, it needs to have a really, 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 really big delta G in magnitude, and it needs to be really thermodynamically favorable. Otherwise, it's not going to function properly. That's why when we were picking our best battery from an earlier video, we always wanted the one with the greatest E of cell. That's why we picked those for our best battery. They are also the most thermodynamically favorable. So that wraps up today's video. Let's do a quick recap. Today we learned how to connect delta G and E. When we did that, we reminded ourselves of what spontaneous versus thermodynamically favorable processes mean. They don't always mean the same thing, right? Spontaneous is binary, thermodynamically favorable is not. We then connected it mathematically using the equation from your formula sheet, and we talked a little bit using an example of what that really meant. Today's video was written, produced, filmed, and edited by Frankie Gennari. I'd like to thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.